Hello students, very good morning. Today we will discuss semester 3rd related to our mathematics topic convergence of sequences, which is our unit 1, in which we are doing one theorem. The theorem is if the sequence of real numbers, that is Sn from n is equal to 1 to infinity is convergent, then Sn from n is equal to 1 to infinity is a Cauchy sequence. Cauchy sequence I have explained to you yesterday in my previous lecture. Every convergent real sequence is a Cauchy sequence. This statement can be written in this manner also. This theorem can be asked in this manner also. Every convergent real sequence is a Cauchy sequence. So here the proof starts. Let limit n tends to infinity Sn is equal to L. Means after solving the limit for this particular sequence Sn, we will get one definite value, that is L. Then for a given epsilon is greater than 0. What do you mean by this? This limit n tends to infinity Sn is equal to L. This means that it is convergent. Means having one finite limit and definite value, then that is called convergent sequence. So here if it is limit n tends to infinity Sn is equal to L, then for a given epsilon is greater than 0, there exists, this is the symbol of there exists, n0 is the element of natural number such that sk minus L, mod of sk minus L is less than epsilon by 2. We have considered here sk minus L, mod of sk minus L, which is less than epsilon by 2, where epsilon is greater than 0. So for all k is greater than or equal to n0, thus if m comma n is greater than or equal to n0, this we are replacing now by Sn and Sn. So here we have mod of Sn minus L is less than epsilon by 2. In place of k, we have replaced this k by Sn. Then it will be mod of Sn minus L, because Mn is greater than or equal to n0. So Sn minus L, mod of Sn minus L is less than epsilon by 2, and mod of Sn minus L is also less than epsilon by 2, where Mn is greater than or equal to n0. Now if m comma n is greater than or equal to n0, then in that case Sn minus Sn can be written as mod of Sn minus Sn can be written as mod of Sn minus L plus L minus Sn. Suppose we open this bracket, then this minus L and plus L will be cancelled. The remaining terms are Sn minus Sn only. So one inequality concept will be applicable here, that mod of a plus b is always less than or equal to mod of a plus mod of b. This is one inequality concept which is applicable here, that mod of a plus b is always less than or equal to mod of a plus mod of b. So that is only applicable here. This equal to sign is changed into less than or equal to sign. Sn minus L is separated here and L minus Sn is separated. Both the parts are written in this single mod. Okay. Different terms means it is mod of a plus mod of b, like this. So mod of a plus b can be written as less than or equal to mod of a plus mod of b. So Sn minus L mod plus L minus Sn mod is written with less than or equal to sign. It means that Sn minus L and L minus Sn can be written as Sn minus L also. L minus Sn or Sn minus L both are one and the same thing, because modular sign is there. So both can be written as with less than sign, not equal to, because this particular term is less than epsilon by 2 and this particular is also less than epsilon by 2. So that can be written as Sn minus L is less than epsilon by 2, so that's why it is less than epsilon by 2, and Sn minus L is also less than epsilon by 2, so it will also be written as epsilon by 2. So epsilon by 2 plus epsilon by 2, if we take LCM, then 2 will be LCM. So epsilon plus epsilon, that is 2 epsilon upon 2, that 2 will be cancelled, then equal to epsilon will be there. So that is Sn minus Sn mod is less than epsilon for all m comma n is greater than or equal to n0. Hence means what? This is only the condition that which defines the Cauchy sequence. So hence Sn is a Cauchy sequence. So this theorem is now over. We have proved that Sn mod of Sn minus Sn is less than epsilon, where for all m comma n is greater than or equal to n0. This is only the definition of the Cauchy sequence. So according to which, hence Sn is a Cauchy sequence. This theorem is now proved. It is over. Now see the next theorem of this unit only. Every Cauchy sequence is bounded, but the converse is not true. What do you mean by this? But the converse is not true. Every Cauchy sequence is bounded, but the converse is not true means that every Cauchy sequence is bounded, but every bounded sequence may not be Cauchy. So this is the part which tells us that converse is not true. So in proof, let Sn from n is equal to 1 to infinity be a Cauchy sequence. Let epsilon is equal to 1 greater than 0. 1 is always greater than 0. So epsilon is equal to 1 which is greater than 0, which is considered by us, be given that this part is given. Then by the definition of Cauchy sequence, we can pick n0 is element of n. n0 one element is picked up from the natural number. So n0 is element of n such that mod of Sn minus Sn is less than 1. Mod of Sn minus Sn is less than 1 for all m comma n is greater than or equal to n0. Now in particular, suppose in particular means what? We may take one particular term out of these two. So we have taken Sn minus Sn0 because m comma n is greater than or equal to 0. We have picked up one, m is greater than or equal to n0. So mod of Sn minus Sn0 is less than 1. Now this can be written in this manner: Sn0 minus 1 is less than Sn0 plus 1. Means this Sn0 plus 1 minus 1 is considered this side and Sn0 plus 1 is considered that side, and Sn is in between. Means what? Sn is in between Sn0 plus 1 and Sn0 minus 1. Means Sn is one particular term which is in between Sn0 minus 1 and Sn0 plus 1 for all m is greater than or equal to n0. So which tells us to consider that small k is minimum of S1, S2, S3 delta dash Sn0 minus 1 in subscript, here it is written in below part, comma Sn0 minus 1. Here minus 1 is in main term only, but here it is in lower script. Okay, Sn0 minus 1. Sn means n0 minus 1. And here capital K is equal to maxima of S1, S2, S3 and so on. Sn0 minus 1 in lower script and then comma Sn0 plus 1 in main script only. Sn0 plus 1. Yeah. So we can assign this as small k and this as capital K. So by using these two, we can write small k is less than or equal to Sn is less than or equal to capital K for all m is element of n. Means what we have considered? Only m. In particular, we have considered only m out of these two. Which tells us that what? Sn is in between small k and capital K. Hence the sequence Sn is equal to Sn n is equal to 1 to infinity is bounded. Bounded means what? It is having lower limit also and it is having upper limit also. So but the converse of this theorem means we have considered one Cauchy sequence. We have considered one Cauchy sequence and proved it bounded. So hence the sequence Sn n is equal to 1 to infinity is bounded. We have taken Cauchy sequence and proved it bounded. Now but the converse of this theorem is not true. It is mentioned in our theorem that the converse is not true. Means what? For example, the sequence minus 1 raised to power n. First of all, let us take this statement, but the converse of this theorem is not true. Means what? Bounded sequence may not be Cauchy. Bounded sequence may not be Cauchy. So for example, the sequence minus 1 raised to the power n from n is equal to 1 to infinity is a bounded sequence. Of course, its minimum value is minus 1 and maximum value is plus 1 for this sequence. So it is bounded sequence. But this sequence is not Cauchy. But this sequence is not Cauchy. Hence, every bounded sequence need not be Cauchy. Because for Cauchy, it is one particular finite value should be there by which this Sm minus Sn is less than one particular value. Right? Maybe epsilon or maybe 1 which we have picked up here. So, but this sequence is not Cauchy. Hence, every bounded sequence need not be Cauchy. So, this theorem is now proved. I have explained you these two theorems which are very important by the examination point of view in our Vikram University. So, please prepare it in a proper manner and do it correctly. And thanks a lot for watching our channel. Please do like it, subscribe it and share it.